Hello everyone, I'm Dr. Buddhika Aliyanike. Today's topic is electronic structure of the atoms problem solving. Let's see the first question. Consider the following energy level in a hypothetical atom. When the electron dropped from E3, energy level 3 to energy level 1, calculate the wavelength in nanometers. So these are the energies given for each energy level. Energy level 4 energy, energy level 3, energy level 2 and energy level 1 energy in joules. Now you can see in this diagram, initially the electron is located in energy level 3. This electron jump into the energy level 1, that is ground energy level. So this is we called emission. Highest energy level to the lowest energy level electron drop. Let's calculate the energy difference between E3 and the E1. This is we called delta E. Delta E is final energy minus the initial energy. This is equal to h nu. H is the Planck constant, and then for nu we can write c divided by lambda. So h times c divided by lambda is equal delta E. Now let's apply the value. E1 energy is given in the table minus E3 energy is negative 5.0 times 10 to the negative 19. This is E1 minus E3 is equal H is Planck constant. It is the constant. We know the value 6.626 times 10 to the negative 34 joules times second. C. C is the speed of the light. It is again another constant value 3.0 times 10 to the power 8 meter times per second, meter per second, divided by lambda. Only one unknown in this equation. So after you solve this, you can find lambda in meters 1.9878 times 10 to the negative 7 meters. But the question says we need final answer to report in nanometers. So 10 to the power 9 nanometer we called 1 meter. So the answer is 1.99 times 10 to the power 2 nanometers. Let's move on to question number 2. What is the wavelength in nanometers of a photon emitted during a transition from initial level is 7th energy level to final energy level 2. So electron jump from 7 to 2, then the wavelength for that emission. So let's apply this equation. 1 over lambda is equal RH. RH we call Rydberg constant. It has a value, it's a constant, times 1 divided by n initial squared. This is initial level, that is 7 squared, minus n 1 divided by nf squared. Nf means final energy level, that is 2 squared. So if we apply values, RH, Rydberg constant value in per meter is 1.097 times 10 to the 7 per meter times initially 7 squared minus the final is energy level 2, so 2 squared. So if you solve this, you can find out lambda. This is 1 over lambda value, and then lambda value is 1 over this value. So it is 3.97 times 10 to the negative 7 meters, or in nanometers. 10 to the power 9 nanometer is equal 1 meter. So 397 nanometers is the emission line wavelength. Third question. Calculate the frequency when an electron drops from 7th to 6th. This is very similar to the previous example. The only difference is the initial level is same, but the final level is not 2. This time it is 6. So same equations we can apply like in the previous slide. Rydberg constant, initially 7, finally 6. So then 1 over lambda value. Lambda is 1 over this number. It is 1.135 times 10 to the negative 5 meters or after you multiplied it by 10 to the power 9, it becomes nanometers. 1.135 times 10 to the power 4 nanometers. This is the wavelength. But the question says we need to calculate the frequency. Then how we can calculate frequency from the wavelength? Applying this equation, C is equal nu times lambda. Nu is the frequency, lambda is the wavelength, C is the speed of the light. So speed of the light 3.0 times 10 to the power 8 meter per second is equal nu frequency times lambda is we already calculated here. So after you solve this, nu or the frequency value is in per seconds, 2.64 times 10 to the 13 per second. This per second is another units we can report hertz. 1 per second we called 1 hertz. So 2.64 times 10 to the power 13 hertz is the frequency for this emission. Go to fourth question. The light with a wavelength of 478 nanometers lies in the blue region. So calculate the frequency of this wavelength, 478 nanometers. We can simplify this equation. C is speed of light, 3.0 times 10 to the power 8. Lambda is given 478. So before we apply this equation, we have to convert nanometers to meters. 10 to the power 9 nanometers equal 1 meter. So after we convert 478 nanometers to meter, divide by 10 to the power 9, then the answer is 4.78 times 10 to the negative 7 meters. To apply this equation then, nu is equal 6.28 times 10 to the 14 per second, or in other units, hertz. Question number 5. The energy of the photon is given. Energy of the photon is 3.72 times 10 to the negative 22 joules. What is its wavelength in nanometers? You know this equation, energy is equal H times C divided by lambda. So H and C are constants, we know the values, and energy value is given in the question. Then the only unknown is lambda. So let's apply the values and calculate lambda. This is in meters, 5.34 times 10 to the negative 4 meters. And the conversion is 10 to the power 9 nanometers equal 1 meter. If you multiply this number by 10 to the power 9, you can convert meters into nanometers. This is 5.34 times 10 to the 5 nanometers wavelength for this photon. I hope now you will understand how to apply the different equations to calculate the wavelength, frequency and energy. Thank you all for watching. Please don't forget to subscribe to the channel for more videos.